Greetings, everyone. This is our second lecture, and I guess the first one where we're going to actually do a little bit of math. You don't like math? Don't worry, it's extremely simple. As I've said before, nothing in this class is very difficult at all with respect to the math. Okay, so in this one we want to talk about descriptive statistics, and I've broken this up into three parts, two core parts, the organizing data aspect, and then the calculating of these measures of central tendency and variability, basically the average, right, the mean, the median, the mode, variance, standard deviation. So the calculation parts will be in part two. And then finally in part three, I walk through a full example where we do everything we've discussed in part one and two with a set of data. So you can see how we would do that from sort of start to finish. Okay, so let's get started. What is the point of descriptive statistics? Like I said before, this branch of statistics is really there to find patterns, to help organize the data. So we need to introduce a few terms to really talk about this. When we collect a whole bunch of data, so you guys have been filling out that Excel spreadsheet to give me data for our future homework assignments. If you look at that spreadsheet, you just see a massive numbers, right? If we just, let's say, look at height or age of the students in our class, either of those two columns, those sections of the spreadsheet, show a range of values not organized in any particular way, so it's difficult to find any pattern that might be there. It's difficult to describe the age or ages of the individuals in our class, or the heights of the individuals in our class, because we don't really see in any kind of patterns here. And so the point of descriptive statistics is really to take those raw scores, right? Those numbers we got directly from that observation or measurement of behavior, or in this case you guys sort of made your own measurement and input that data. We take those raw scores and then we look at them in their larger grouping, what we call a distribution. Okay, we see how they spread out from low to high. We see where they group. There are a lot of scores close to one particular value and then not very spread out from that value. Do we have a huge spread way away from that center average, right? And so that's really the whole point of descriptive statistics, is to sort of summarize, to organize, to get a description, a picture of what your data say. And so to that end, we use some graphing as well. We'll talk more about graphing in a subsequent lecture, but graphing is going to emerge at least a little bit here in this one as well. Okay, so to that end, a frequency table. So if you're collecting data on a particular thing, let's say who here likes pizza versus spaghetti versus chicken wings versus a salad versus I don't know, pick your favorite foods, throw them on there, and we go around, we just ask a survey, okay, who likes this one the best, right? You can only pick one. We would get a bunch of tally marks next to each of these telling us the frequency that each of these values on this variable we might call favorite foods variable, right? A very nominal variable. There's no order to the points on that scale. We would get a whole list then of frequencies, and we would need some way of displaying those so that we could see whether or not particular values, say pizza, is higher than more of the other ones. Right? So let's walk through an example. This is just the steps of creating it. Basically, you find the highest and lowest scores, you create two columns, you list the full range of values, put the scores for each value. I think it's easier to go through these steps using the example itself. Okay, so you can just come back to this if you forget the steps. So let's say you have a list of 14 IQ scores for a gifted classroom in a particular elementary school, right? You don't know the students, it's all anonymous, but you were given this IQ data, right? And so I've already put it in order from lowest to highest just to make it a little bit easier, but you probably expect that this would come in even more randomly, right? These are raw scores. So we have a 127, a 127, a 128, 3 129s, 2 130s, a 133, a 136, a 136, a 138, and finally 2 140s. Okay, so first step we have to do is identify the lowest and the highest score. So since they're in order, that's easy, 127 to 140. So we want to create a column then that lists all of those values from 127 all the way to 140. Okay, so I do that. I write down a column, write IQ at the top so I know what the variable is, and then I list 127, 128, 129, 130, all the way down to 140. Now we just need to simply list the frequencies of these. Note you have all the values in there. So if you look over at the data, nobody in that classroom had an IQ of 131 or 132, but they still get listed in that larger table, okay? Now we simply record the frequency. There were 2 127s, so we put 2 in that column, right, in that particular cell. There was only 1 128, there were 3 129s, and then notice for the values where nobody had that IQ score, we put zeros in those places. So you list the entire range of scores, and then you simply count up how many times those particular values occurred in that distribution of raw scores, and you plot that frequency here, right? Now, with these sorts of organized data, with this frequency table, you can see we have a little bit more information now about how frequently certain values occur. You can see for the most part, the bunching or grouping of scores is closer to the 127 to 130 range rather than the, say, 136 to 140 range. You can see the most common score, in fact, is 129, followed closely by 127 and 130, and then a couple of scores like the 136 and 140 that also have two occurrences. So again, seeing it in a frequency table does a little bit to bring what was first a sort of random pattern of numbers. It's difficult to see, I should say, that pattern into focus a little bit more. Now, another thing you can do with this is calculate cumulative percentages. Now, cumulative percentages are basically like percentiles. So I don't know if you've ever been told that you were in the 90th or 95th percentile for something. Say you took a test, a standardized test at one point, and it said what percentile. Percentile is saying in that whole population of individuals that took it, right? Or in the sample, you could calculate a percentile for that. But in this case, the whole population of individuals that took that exam, if you're in the 95th percentile, it's saying that your score on that exam was at or above 95% of the rest of the population. And so that really is what we would call a cumulative percentage, right? If we add up the percentages as we go higher and higher up in the scores, and so it was 5% and 10%, you know, let's in fact see that with those data, and it might make a little bit more sense, okay? So take that frequency table we already had. We know that there were 14 scores, and you can even add them up in the frequency column just to double check that you caught them all, right? Now what we want to do is list the cumulative frequency, meaning if there were 2 scores at 127, when we get to the next value of 128, since there's one there, we add that to it because there are now 3 scores at or below 128. When we get to 129, we add 3 more in there, right? And so here's what that cumulative frequency would look like as we continually add whenever we encounter values, occurrences of a particular value. So 2 gets to 3, gets to 6, gets to 8, and then because we have zeros for a couple, it stays at 8, gets to 9s, 11s, 12s. So how do we get to cumulative percentage then? Well, we simply take the value listed in cumulative frequency and we divide it by that total of 14, right? The same way you would normally get a percentage. And so what you can see then is the percentile of somebody with a score of 127 is 14. Right, saying they are at or above 14% of the population of individuals in that gifted class. But if you look at somebody who, say, got a score of 136, right, 2 people got that score, their percentile is a 0.79 or 79%. They're at or above 79% of the population. That's particularly informative because it not only tells you where you scored on the exam, but if you were at 128 and you were in the 95th percentile, that would be better and more informative than simply knowing you had 128 and that was a good score, right? So percentiles can be really, really useful ways of learning more information about your data. Now, sometimes, and this is bordering on an example that would qualify here, sometimes you might have a lot of values. So in this case, we only went from 127 to 140, but that's because I made up those data. If we collected data from a larger range of individuals, say we included not just the gifted class, but all classes, we'd probably have some IQ scores that were a little bit lower than that. And so let's just take a hypothetical where our lowest IQ score is 100, and our highest IQ score is this 140. In that case, we have 40 values to represent instead of the 14 that are listed here. So imagine what this slide, this screen, would look like if I had to list all those values from 100 all the way to 140, plus all of their frequencies, then their cumulative frequencies, then their cumulative percentages. Would that organize the data? Would that make it more clear? Arguably not, because there's so much information then still there to try and look at. And so when we have that huge range in values and we're trying to create an expected frequency table, a frequency table or frequency distribution table, then what we frequently do is do what's called a grouped frequency table. It's easy to do. You just take a range of values, say 125 to 129 or 126 to 130, right? And so let's do that. So 126 to 130, if I just bunch those together into one row, I can count up all the scores that were in that range, and there were 8. 131 to 135, only 1 of them. 136 to 140, 5 of them, right? So an interesting distribution. More of them towards the low end, another chunk towards the high end, and very few in the center of the distribution. So group frequency tables are really useful for taking those big data sets, right, those large ranges of values, and crunching them down a little bit so that we can see it a little bit better. When would you use this? Well, particularly when you have continuous or interval ratio data, right? I mean, those continuous variables can be presumably any value at all in between whatever the low and the high end score is. So it can cover a huge data range. So when you're trying to determine the number of intervals, this is probably a little bit too few, the 3 that I used here. You want to shoot for somewhere between 5 and 10. Right, 5 and 10 is easy for people to sort of understand the patterns and see those patterns. More than that, and you're really not doing justice by grouping it. Right? You've left too many groups still, probably. So let's talk a little bit about graphing then. How might we take that table and turn it into a graph, a visual depiction? Visual depictions frequently are easier to understand than simply numerical tables. Not always. But one way in which we can take frequency data, like the data we've been looking at, and visualize it is in what's called a histogram. So I don't know if you've ever been shown by a professor a graph depicting the range of scores on an exam. Right? If you've ever seen that, it almost definitely was a histogram. And you'll notice in memory that the height of the bars was supposed to indicate the number of individuals that scored at or near that particular value, that score on the exam. And so really the graph is simple. You have frequency on the y-axis, and then you have whatever your variable is down there on the x-axis, right? Whatever we were depicting. So in the previous example, we were depicting IQ scores. So IQ scores would be on the x, and we'd have frequency on the y. Histograms always have frequency on the y because a histogram simply depicts one continuous variable on the x-axis and frequency of those values on the y-axis. So let's see some examples here. The bottom left corner here, very clear reflection of an exam score distribution. Oftentimes, histograms are likened to sort of a cityscape, and that's because they are bar graphs. Right? You draw a bar up to the height of whatever frequency is for that value. So in this graph down here, we see that for scores in the range of 0 to 20, that was the lowest frequency, maybe somewhere around 3 or 4 it looks like for the height of that red bar. And then for scores between 20 and 40, we see an increase in frequency with that pink bar, the yellow bar for 40 to 60, and then the most frequently occurring bracket of scores there between 60 and 80 in the green bar, and then goes back down a little bit for the blue bar for 80 to 100, okay? Note that these bars are touching. In a histogram, the bars will always touch. And that's because the x-axis is a continuous variable. That means as you go from 0 to 20, then you go to 21, 22, 23, 20. There's no gap between those values. Okay, and because there's no gap between those values, there's no gap between those bars. The bars will touch on their sides. That is one of the hallmark features of a histogram. So make sure you note that because you're going to create a histogram for me. You're going to show me how you create a histogram using some data that we collect. Later on. No, you have to label your axes. Make sure you label your axes. X, Y, not just the letters, but what those variables are. Be careful when you draw your graphs. Use a ruler if you have to, right? This is a college class. This is not a comic drawing sketch class. So let's get it right. Let's make sure we get some clear pictures of this so that I can see that your graphs are done right. And really, it's pretty easy, right? This is a very, very simple bar graph. So how might we do it with the data that we had? Well, we take our IQ and our frequency table, right? And what I like to think of is that you just kind of take this table and rotate it. So, right? And once it gets rotated, you can kind of see that we have IQ running across the bottom, just like our x-axis is going to be, running 127 to 140. And then the column, which is frequency that is now on top, represents the height of each of those bars. One goes to 2, this one goes to 1, this one goes to 3, this one doesn't go up at all, this one doesn't go up at all, this goes up to 1, right? So let's see it. Those data turned into that graph, right? So pretty straightforward. Notice that you do not draw a bar if that particular value on that X variable, in this case IQ score, did not occur in those raw scores, in that distribution of raw scores. So there were no 131s or 132s or 134s, 5s, 7s, or 9s, right? Those scores did not occur. But you don't skip them. You can't do that because then you're not representing that x-axis variable properly. That value exists on the scale. We just didn't have any of them. And so leaving it blank shows that gap, shows that those scores weren't in that larger distribution. Another way of depicting essentially the exact same information is what's called a frequency polygon. Instead of a bar graph, at the top of where you would put those bars, you put a dot. And so instead of the bar itself, if it was supposed to go up to 2, you go up to 2 and you just draw a dot up there at 2. And then, as you move across, you connect all of those dots. Remember that if their value is a 0, put a dot down at the 0 at the bottom of right there on the x-axis, so you remember to go down there. Looks a little bit more like a mountainscape as opposed to a cityscape, right? You can kind of see, right, more peaks. You can see the comparison then, histogram on the left, frequency polygon on the right. They essentially are depicting the exact same, not just essentially, they are depicting the exact same information. So when you look at it like this, especially that frequency polygon, you can begin to see how that distribution spreads out, how it's shaped, whether or not a large number of scores is grouped around a particular center point, like an average or a mean, or whether or not they're spread completely. That really gets us to shapes of distributions, okay? And one of the most known shapes of a distribution is what we would call the normal distribution, frequently referred to as the bell-shaped curve, though there was a rather racist book that was called that. So I prefer to just think of it as the normal distribution. And so the normal distribution is supposed to depict all the frequencies. It's just a frequency polygon, but imagine it's for a population. So instead of these jagged points, you've got so many scores that it's really starting to fill in, right? Every spot in between, there's somebody there. You don't go all the way back down to 0. And so what it's depicting is the way in which most things that we can measure are spread around the average. So the center point of that distribution, the highest point in that normal distribution, the highest point in the curve, is the highest frequency. And in a normal distribution, it's symmetrical. That is the average of that population. And how it spreads out is by scores that are away from that average, that are close to the average at first, and then farther from the average, and then way far from the average. Very, very different from the average, right? So think about the way most of your professors look. I probably don't look like most of your professors. I got my hair up in a bun right now, but it's really kind of long, right? I wear tie-dye most of the time. Hell, I got a nice jacket on, but I'm wearing a Star Wars shirt underneath, right? And so I am not near the mean or the center of that distribution. I'm way off on one of these tails, depending on whether or not weirdness is a number that goes up or down, right? And so my point here is that the normal distribution tries to reflect that frequency, and that's why, as it gets further and further away from the center, the bars go lower and lower and lower, right? The lines get lower and lower and lower, because those extreme scores that are far from the center of a distribution, far from the average, are rare, right? They are extreme, they are unusual, and we can use the normal distribution then to really determine how far something has to be from the average to say, okay, that's weird, we need to look into that. Okay, that's definitely something unusual, and it might be significant in some way. Okay, so it's really just a frequency polygon, right? It's just based on a huge population of scores, and so it's smoothed over. And what we see is that so many of the things that we can measure, almost anything we can measure, in fact, looks like the normal distribution when we measure enough people, or we look at what's called the distribution of means. But that's jumping ahead a little bit. Now, in the few times that it's not a normal distribution, let's say you gave somebody an exam. Right? You gave the whole class an exam, and the exam was super duper hard. Just incredibly hard. That means most people are going to score fairly low on that exam. You still might have one or two that score really, really well for whatever reason. They studied in the right way, they had the right sleep the night before. And so that top figure there that represents a positive skew, notice that the bulk of scores, the highest hump there, is lower on that x-axis, lower down, so over to the left-hand side a little bit more. And then the tail represents one or two extreme scores way over there to the right that were farther that direction than the other direction or near the center. That's a positive skew, because if we think about that x-axis, that gray bar at the bottom, as going from low values up to high values, then it's going to go to higher and higher, more positive values as we go over there to the right. So the tail's pointing to the right. That's what we would call positive skew. In this case, we might call that a sort of floor effect, right? These individuals, most of them are bunching up near the bottom because it was so hard they can't really get a whole lot lower, right? There can't be an extreme score in that direction because they're already near the low end of the scale for the exam scores. You can't have these few that go in this direction. You could also have ceiling effects. So let's imagine the thing I'm measuring is just too easy, whether it's an exam or it's a problem-solving thing as part of an experiment. And then most scores are way up there at the top. But a few people really weren't paying attention. They still scored really, really low. Now we have a ceiling effect. They can't get much higher than that. The tail points towards the lower values. It's negative skew. All right? So positive skew, negative skew. We can also have shapes of distributions that are still symmetrical, but are not normal. So if we talk about it in terms of what we say, refer to as kurtosis, kurtosis is, as it says, the degree to which the width and thickness of the tails deviate from the normal curve. So the normal, in terms of kurtosis terminology, would be mesokurtic, right? Meso is in the middle, kurtosis is the shape or skew of the distribution. If a flat distribution, where scores are way away from the mean, spread in both directions really widely, not a whole bunch of them near the center point of the average, we call that platykurtic, like a big flat wide platypus, right? If, on the other hand, everyone is right near the mean, we're all bunched right together, we call that leptokurtic, right? The tall, thin distribution. This isn't my graphic. I never knew this mnemonic except for the platykurtic one. But the leptokurtic works. Think about kangaroos, super tall, heads together. Kangaroos leap, right? Lepto. And then you get this tall, thin, skinny distribution where all the scores are near the center. Okay, so that's how we begin to organize our data. That's how we can take some frequency information and immediately turn it into both tables and visual depictions in terms of histograms and frequency polygons, and then the introduction of this normal distribution. Okay, so in the next video, I want to talk now about how we calculate some of these measures of descriptive statistics, measures of central tendency, measures of variability. All right, so that's it. Cheers.